Well, hello to everyone out there joining us from around the world. Welcome to hour number one of our 3-hour ECL workshop at Community Day 2021. My name is Jason Momoa, and with me today is Antonio Banderas. No, not just kidding about that. Of course, my name is Bob Foreman, and with me is Hugo Watanuki. We are senior software engineers and ECL trainers. Just wanted to see how many people were paying attention. We both work on the ECL training team, and we're excited to present this year's theme, which is Cruising the ML World with HPCC Systems and ECL. Now, I know that most of you listening are still working from home and probably restricted at your location due to the current pandemic, but we hope you will enjoy traveling with us in the workshop through 6 of the most popular machine learning bundles currently available. So think of us as your cruise directors as we enter the land of the machine learning world. The land of the machine learning world. That was interesting. All right, so buckle up. Let's go. Let's get started. So in each of my workshops, I'm going to give you a nice, interesting travel quote to think about and meditate on during that hour, during our first hour. I chose one that's always been in the back of my head, especially when we all went into a lockdown. This is one of my favorite songs of the Moody Blues. It goes way back. It was called Best Way to Travel. And of course, the travel quote of the day is thinking is the best way to travel. So we have a lot to think about in this hour one workshop, and let's move on and get started. Now, I'm going to start with just a very brief introduction to machine learning so that those of you that have never tried it or never delved into it, you've read about it, but you've never really tried it, and particularly with ECL. I'm going to give you just a quick overview of the terminology and how we translate what's going on in the machine learning world to our ECL world. So a lot of these slides I'm going to borrow from my mentor of machine learning and my data scientist, Roger Dev. He had presented something probably about 3 or 4 years ago, and I'm just taking the highlights from his presentation, and we will review some of the terminology that he presented way back then. All right, so machine learning, the learning part, has several categories of machine learning. The most common type of machine learning is supervised, and we're going to talk about this in the hour 2 workshop starting tomorrow. But and the reason why was because it was a little more involved, a little more detail as far as the implementation and working with it. So we wanted a little more time for that one. That's why in hour 1, we're going to start with probably I believe to be the more simpler of the bundles, because they're very easy to implement and there's very little parameters that you have to be aware of. So we're going to be talking about unsupervised learning today, 2 of the most popular machine learning unsupervised methods, which are K-Means and DBSCAN. On hour 3, we're going to talk about the land of neural networks and deep learning, and then also wrap up our hour 3 workshop with a look at an ensemble method, which is using boosted regression forests. So here's another visual view of some of the many machine learning algorithms that are out there, and today we're going to be focusing on unsupervised learning, and in a subcategory, something called clustering. So there's other types of unsupervised learning like dimension reduction and pattern search. We're going to be focusing on the clustering of records into common clusters that the machine learning algorithm translates as being related. So let's start with the basics. Let's start first of all from the land of ECL. Now, all of you know what a record the record structure of different fields up to a certain length. And also part of that record structure could also have a target value combined in a single record structure. So we slice out the fields the part of the fields that are going to be used to analyze our machine learning model and create our model. These are called independent variables. All right, so the fields in the independent are also called features in machine learning. All right. And then what we're trying to predict is called the dependent variable. And this is kind of funny because when I first learned ECL from my colleague Richard Taylor about 10 years ago, every time I said the word variable, he would probably throw something at me because ECL is a declarative language and we talk about data definitions. And you all know that fields are field definitions. But we can loosen it up a little bit when we talk about machine learning. We can talk about these things as variables, quote unquote. And then, so I'm not going to penalize you if you throw that word out with me during a machine learning session. All right, so when you combine the independent, which are our features that are going to be predicting the model, building the model, and then the dependent data combined, we call that the training set. And then when we want to, of course, test the model that's been created, then we call that the test set. The encapsulated learning is known as the model. All right, so everything revolves around a model, building a model. Every single bundle builds some kind of a model. And this model represents a hypothesis that regards the relationship of the independent to the dependent variables. And also a hallmark of machine learning, another term you'll hear is generalization. So here's the idea. The training data will have certain values, and we use the training data to build our model. The idea of generalization is that when we then test it and use prediction on new data coming in, even though that new data might be completely different than the training model, the training set, the model will be smart enough to translate that lots of different data can come in, and based on our training set that we use to build the model, this new data coming in will fit, and then we'll get a more accurate prediction. And when that doesn't happen, that's another term that we'll talk about in later hours of the workshop called overfitting. All right, so here's a conceptual example of machine learning. So Roger used this about 4 years ago when he was introducing machine learning at one of our summits. We talked about trees in a forest. So we have certain characteristics of a tree: its height, its diameter, its altitude, and rainfall, and then age. The first four fields can be easily measured using some kind of a gauge like an altimeter or a rainfall gauge, or even just a tape measure for the diameter of the tree, and then a laser pointer or something for the height of the tree. But age is a little tougher. To determine the age of a tree, sometimes the only method is to cut the tree down and count the rings in the tree. And of course, we don't want to kill the tree. So we're going to learn a model using height, diameter, altitude, and rainfall, which we're going to call our independent variables. And then we're going to predict the age based on the other four independent variables. And so from the start, we say, well, how would we construct a model here? How would we build the model on this? Well, machine learning, we'll pick a bundle. We'll pick one that's kind of thinks that looks like it's going to fit. In this case, it might be a decision tree, a learning tree, no pun intended. We're doing trees in the forest, and we're going to pick a learning tree bundle. We could use linear regression on this one. We could use a number of ones. And a lot of that, Rogers says that a lot of times picking the right bundle is more of an art than a science. So we pick a bundle, we construct the model, we see the results, and if the results aren't good, we move on to another bundle, or we tweak the parameters a little bit to see if we can get a better result. All right, so depending on the algorithm, we can get insight into relationships between the independent and dependent variables. This is also known as inference. And again, a good best practice is that we want to have as our dependent variable sometimes the ones that are hard to measure. Like we don't want to chop the tree down to measure the age. So we have observable features that we can easily look at and analyze. Also, notice the nature of this data is all numeric. More about that in just a few slides. So here's some more terminology regarding machine learning. We talk about models being either quantitative or qualitative. So when we talk about a quantitative model, it's more of a scalar value, a numeric value like the price of a house, the numerical age of a tree. Qualitative is more of a classification issue, like what species of tree is it? Elm, oak, cedar, and so on. Or it could be binary. Is the tree healthy or not? All right. So we have, for quantitative model, we call that also regression. Those terms parallel each other, are used in tandem with each other. So sometimes when I say I'm using regression, I'm also using a quantitative model. And of course, then the qualitative model is also in tandem or in parallel with the term called classification. So, all right, so that's the terminology, real simple. Just a quick overview of that. If you want more, you can go out to our blog on HPCC Systems, and you can, from there, view any number of great blogs by Roger Deb and Lily Zhu, who are our two data scientists working on our machine learning bundles. So during these workshops, we're going to present with you some tutorial code. And this code is available on GitHub. You can download it at the end of this workshop, and you can also download hour 2 and hour 3. They'll also be available. And you can then load them up on your machine and actually follow along with us as we go through these workshops. So how do you get started with that? How do you get the code that we're going to provide with you? How do you install these machine learning bundles in particular? So the first thing you need to do is you need to have your HPCC Systems client tools installed on your system. And remember, you can have multiple copies of client tools, and I recommend strongly that you always use the most current version of your client tools. So machine learning is pretty much platform independent, but occasionally they may say this bundle requires version 7 or greater, or even maybe down the road version 8 or greater. But for now, most bundles are platform independent, but I always say as a best practice, install from the most recent client tools that you have in your on your machine. All right, so for example, on my machine, I've got program files x86, HPCC Systems 8.2.4, client tools, and then bin. So I navigate to that directory, and then from that directory, I then write this script, ECL bundle install, and then the name of the Git file. So the first bundle that you're going to want to install, even before you use any bundle, is the ML Core. The ML Core has many functions and tools that allow you to easily interface with the ECL world and the machine learning world, converting your ECL data into a machine learning format, sequencing your data automatically, analyzing your data using a number of analysis tools that are built into ML Core. So this is the first one you always want to install. In the next two bundles, the next bundles that we're going to be working with today, it's also supported with PB-BLAST. Now, PB-BLAST is an acronym that means Parallel Block Basic Linear Algebra Subsystem. Parallel block basic linear algebra subsystem. And this provides distributed scalable matrix operations that are used by many of the bundles, almost all of them. And they can be used directly whenever the matrix operations are in order. And like I said, these bundles have a dependency on this PB-BLAST bundle. So that also has to be installed on your system. And then the other two bundles, K-Means and DBSCAN, because we're targeting these. These are the unsupervised clustering machine learning algorithms that we're going to be demonstrating in this hour workshop. And so remember, for PC users, make sure that when you go to the command line to run these ECL bundle scripts, that you run it as an administrator. Some of you with managed machines may need to contact your help desk to get them to give you, because you may not have the rights to install these. You need to contact your help desk and have them install these bundles for you. All right, so now let's talk about the fundamentals of machine learning, which we're going to be talking about this in all three of our workshops. The first and most important thing, and probably the most amount of work that you're going to do, is preparing your data. And I talk about preparing your data, the best practices that some of you already know how to do in ECL. I mean, cleaning your data, and I also mean removing fields that may not be applicable to your machine learning model. And then the other phase of preparing your data is to move the data from the standard ECL record structure into the record format that is required by machine learning. And we have a number of functions that are already built into the ML Core bundle that help you do that. All right, so now this slide looks like we have traveled to Brazil. My colleague Hugo wanted to show this to you for this first bundles, the two bundles that we're going to be showing you today. We're going to be working with the exact same data set, which is really cool because you'll see how both bundles respond to the same set of clean data that we're going to be applying to it. And this data comes from the city of Sao Paulo in Brazil, and is actually, we're concerned with property taxes. So we have a geographical area of these homes, and then we have this property tax that's available there. And then here is the property tax formula that is described on their webpage. These webpages actually work. You can download this data for your own, but we're already going to give you this data in our workshop, so you don't have to do that. We saved you that trouble. But Hugo also wanted just to show you the complexity of what's going on with the original data, and then the amount of ETL that was necessary to convert this data from its raw data format into its form that was then applicable to our machine learning algorithms. All right. So we're not trying to teach you Portuguese here. We're just trying to show you the amount of ETL work that was put into this example data. And so here's just a quick graphic of the raw data input. You can see here that we have dates and we have string information and some other stuff that's in string format. And after all of the ETL that we do, we reduce it down to a set of numeric values. And now the machine learning algorithms say, we're ready for this. Let's do this. All right. So again, as a review, unsupervised data, and for that matter, supervised data and even neural network data, all machine learning bundles should contain all numeric values, and recommended your first field of your record is a numeric and sequential ID. In most cases, sequential will work better. There will be some exceptions where sequential sequencing is not needed, and I mentioned that specifically in the workshop where it is or it isn't needed, or in the examples where it is or isn't needed. All right, so let's move on here. Preparing our data, we have to have it all numeric. And then we're going to separate our data into training and testing. Hugo's going to show you that. Here are the machine core functions that allow you to sequence the data, append sequence ID or SEQ ID. And then the ToField function is one of the many functions that are built into the ML Core bundle that convert our raw data into the numeric format that's required by the model. Okay. And there's other functions in there too that we talk about in later workshops. All right, and by the way, the ML data is a definition that's returned by the ToField function that you can then use in additional functions that require that data for analysis and prediction purposes. All right, so real quickly here, let me talk about DBSCAN and K-Means and clustering, and the concept of geospatial clustering, clustering by distance. Here's an example. You're a food delivery chain, some kind of a pizza place, and then some areas of town like pepperoni pizzas, other areas of town like the white pizzas and so on. So you can actually, by clustering and looking at the preferences of your customers, then stock up your individual stores. If you have more than one, if you're a franchise, you have more than one store, you can stock up one store with certain ingredients versus another store based on the demand of the customer. All right, another good use of this is the effect of natural disasters, plotting location of weather stations in a city. All right, and this can be used also for handling outliers. And then here is some other use cases, and we've got document classification, delivery store optimization, crime localities, high crime areas, segmenting our customers. Fantasy League, it's that time of year, isn't it? Fantasy League stat analysis. insurance fraud detection, rideshare data analysis, taxi information, cyber profiling criminals, record detail analysis. Actually, we have an example of that in our ensemble in hour 3. We're going to be working with record detail analysis for a phone bank, and then automatic clustering of IT alerts. So by the way, here's the website where I got this information from, called 10 Interesting Use Cases for the K-Means algorithm. But also this can apply to DBSCAN. So in our tutorial, I've already showed you how to install the bundle. And then Hugo's going to show you a little bit about the numeric field format and how to convert that, and then training the model, which is normally called a fit function. And then how do we assess the accuracy of the model? Number of clusters, outliers, something called the silhouette coefficient, which is part of the machine learning core. In summary, if you have a -1 for a silhouette coefficient, that means it's the worst score possible. 1 is the best score, and so you might have a value somewhere between -1 and 1, and there's a mathematical formula behind it. All right, so and then at the end of this, we're going to compare K-means advantages and disadvantages to DBSCAN advantages and disadvantages. So in our DBSCAN bundle, once again, DBSCAN is a density-based unsupervised machine learning algorithm. It forms clusters of data points that tend to migrate closer together. All right, so the beautiful thing about DBSCAN is that sparse data, or what we call noise, will get removed from a cluster. But then you have to be careful. Sometimes these outliers can then be rebels on their own and form their own clusters. So we're going to examine, again, working with the DBSCAN algorithm, then compare it with K-means. And the beautiful thing about the algorithms is that they are made for HPCC systems. So they run well on any size cluster, which is a wonderful thing. So you can test it on a small cluster and then load up a bunch of data and test it on a much larger cluster. So DBSCAN, the first one we're going to look at, is density-based spatial clustering of applications with noise. Like noise you've heard for the last 20 minutes from me. Noise in this case is records that just don't particularly fit a cluster, or maybe the data is a bit sparse. So we don't have enough information about the data. So the principle of DBSCAN is to find the neighborhoods of data points that exceed a certain density threshold. And then there's only 2 parameters that you need to worry about. Our epsilon parameter, which is the center point of the neighborhood, the radius of the neighborhood, and then the minimum number of data points that are required to say, I have a cluster. All right. So the DBSCAN uses something called a find and merge process. So what it first does, it starts by finding one big neighborhood, and after one cluster is found, it will start the same process with another random point and begin and maybe form another cluster. And the process continues until DBSCAN finds all of the other clusters, and then data points that don't belong to any cluster are identified as outliers. So DBSCAN is excellent for exploratory analysis. In other words, I don't know exactly what I'm going to do with this data yet, but I just want to see how it's all shaping up. All right, so let me move on and go through this very quickly. The DBSCAN parameters, the epsilon, of course, and minimum of points. You see these default values of 0 and 2. And then the method of the clustering, which defaults to Euclidean. But there's also cosine, Haversine, Chebyshev, Manhattan, Minkowski, okay? And then, of course, we have the fit function, which performs the DBSCAN clustering on the data set model that you've defined in the DBSCAN function. And so once we do the clustering, then we analyze it with the number of clusters and the number of outliers. So that's how simple it is. And I ran a little bit over there, Hugo, so I will try to speed it up in our next little presentation. But there it is, sir. I'm going to go ahead and turn it over to my colleague, Hugo. I'm going to stop sharing my screen right now and let Hugo enable his ECL IDE. And Hugo, you are on the floor, sir. Thank you very much.
Thank you so much, Bob. And hello everyone, welcome to the first tutorial of today's workshop. My name is Hugo and I will be guiding you through all the tutorials we have scheduled for this 3-day workshop actually, right? So the main purpose actually of all of these tutorials is to apply the concepts that Bob will be bringing during the lectures and actually apply them into a real life or a practical situation on addressing a problem in real life. And today we'll start with DBSCAN, but before we start, just want to make sure that you guys have all the prerequisites in place, starting with the code examples that we have shared. So you can see here on my ECL IDE that I have a couple of code examples under the Hour 1 folder, and that's all the code examples we will need for today. And also make sure you have your bundles showing up under the bundles folder in your repository. Specifically today, we are going with DBSCAN, K-Means, and the prerequisite for both bundles, which is the ML Core bundle. Okay, quick assessment here. And also, if you have any questions throughout the presentation or the tutorial, feel free to post your question in the chat. Myself or Bob will promptly answer you, okay? Very well, so what's the purpose of this first tutorial? We will pick the data set that I'm sharing on my screen, the tax records for properties in the city of São Paulo. And we will try to apply DBSCAN and see if we can cluster the data. Because this data set contains not only attributes regarding who is owning the property or where the property is located, but it also contains numeric attributes from the property, such as what is the land square footage, how many floors the construction has, or even what is the assessed value for the land and for the building. And of course, if we can cluster this data using these attributes, and at some point in time, we can add meaning into these clusters and potentially find outliers. Properties not sharing common attributes with groups of properties that are should be closer to it can be considered outliers and could potentially be looking into potential tax evasion. So that's one of the possibilities for using DBSCAN or the clustering methods we will see combined together. Okay, and this is actually a two-part tutorial. First, we will use DBSCAN to cluster the data, and afterwards we will use K-Means to get some more granularity on the outliers for this data. Okay, so starting with the file housing ECL file, that's where we have the raw record structure for our data set. And you can see here we have more than 40 fields, all in Portuguese, because this is coming from São Paulo City Hall. But I am just selecting here the numeric fields that actually represent attributes from the properties in regards to how that property is characterized, assessed, or even the geographic location of that property. And this has all been done with the support of a construction engineering student that has actually added some knowledge domain into that selection process. Okay, so starting with all these fields, I have labeled them as double precision floating point numbers because we will be working with standardized values later on. Okay, and to transform the data, initially we have this prep01 file, which will allow us to do a series of transformations on this raw data set. I start by adding a random field into that data set. This is a very important tip. You will be seeing us doing that throughout all the tutorials. You never know if you're working with raw data if there is any skew originally in the data. You don't know if the data has been sorted in a certain fashion. So to make sure you don't carry over any bias under your supervised or unsupervised learning, make sure you add a random field into your data set and add a random number into that field, and later on sort your data set by that field so you can eliminate any potential skew in the data. Okay. With that, we basically cast all the fields, all the original fields into real, and I'm making give you guys a tip here. I'm also converting all the original labels from Portuguese to English, so you can easily see what is behind each attribute. And then I'm projecting my original data set against this transform structure, sorting the data by the random field to eliminate any skew and shuffle the data. And finally, I'm extracting 5,000 records just for the purpose of this tutorial. I could use the entire base, if you will, for a practical purpose, but just for the tutorial purpose, I'm going with 5,000 records. And if you want to see how the data looks like after this first transformation, remember, we have this BWR here that you can basically keep uncommenting all the output statements and see how your data is being transformed. And to start with, I have here how the data set looks like after this first round of transformation. Only numeric fields as double precision floating point numbers. Okay, but like Bob has emphasized, the machine learning bundles require your data to be in a specific format that we call machine learning data frame. So in order to help us convert our transformed data set into the machine learning data frame, we have a convert02 ECL file that leverages the machine learning core functionalities to help us convert the data into the machine learning data frame more easily. So to start with, I'm just importing the machine learning core bundle, and I'm starting with appending a sequential ID into my transformed data set. And I'm labeling that attribute as rec ID. So you can see by uncommenting this output statement over here that all that function is doing is actually adding this leading field into my transformed data set in a way of preparing my data for the data frame expected by the machine learning bundle. And the second function that we are going to use here is the ToField. And you will see this function pretty frequently in all of our tutorials. So this is the first time I will show you what a ToField function is doing. It's basically making a matrix conversion from my relational database into a machine learning data frame. So if you uncomment this output statement, you can see here, this is how the machine learning data frame looks like. Basically, I have under the ID column, each one of my rec IDs. And on the number column, I have each one of the attributes that I'm taking into my machine learning bundle for some learning. And in the value column, I basically have the respective values for each attribute. Okay. But if you have some math background and you are looking at this machine learning data frame, you might have noticed that I'm dealing with different magnitude of values here. For instance, the city zone is usually a small number, but the assessed value for the land and for the building are usually numbers in the ranges of thousands. So if you take these raw numbers into your clustering algorithm, you may end up getting some skew on your clusters. And to avoid that, we will try to standardize these values, which means we are basically taking the average value of each attribute and subtracting the mean from the original value and dividing by the standard deviation. And you might be thinking that it could be a lot of effort, but again, rely on your machine learning core bundle for any pre-processing. And we are using here the field aggregates function that gives us some basic statistics on all the attributes from our transformed data set. Just so you have a look, you can just go into our BWR file, and here is the report from the field aggregates function. You can see for each of the 15 attributes we are taking into our learning activity, I have some basic statistics, and the most interesting ones are the mean and the standard deviation. Okay. So going back to the convert02 ECL file, I basically defined a function to do the calculation for the standard deviation using the my aggregates results from the basic statistics provided by the machine learning core bundle. And using that function, I basically calculated the standard values for each field using a project transform function. And lastly, I converted the values back to the machine learning data frame and selected only the first 13 fields, or the first 13 attributes. And remember, that's because I don't need to cluster everything in my data set. If we go back to our BWR, we can see here that these are the standardized values for each attribute, but I don't need to standardize the values for the property ID and the zip code, because these are actually attributes that I will utilize afterwards to trace back which outliers were identified and where it's located in the city of São Paulo. Okay, so more like a practical reasoning for not clustering those two fields. Now, this is how the machine learning data frame looks like after all these transformations. So once again, I have each rec ID under the ID column, the 13 attributes I'm taking forward for clustering, and the standardized values for each attribute. Okay, so now we are ready for some training, and that's why we have the train03 ECL file, DBSCAN, where the core magic will happen. So first thing, import your DBSCAN module, and I'm taking my training data. Remember, this is already in the machine learning data frame format. And I'm using the feed function that Bob has just presented to you and passing my train data as an input. I will come back later to the input parameters that we can put in DBSCAN, but for the time being, let's just look at how DBSCAN has clustered the data by outputting the model provided. And I'm also taking a step further and outputting all the records that were associated with the label 0, which means they were actually outliers from the clustering activity. So if we look at our work unit results here under the model tab, you can see each of the rec IDs end up being associated with a specific cluster. In this case, cluster number 5, cluster number 4, and 3. And I can also see the outliers. So rec ID 86, for instance, was considered an outlier. That's why it's labeled as 0. Now, you might be wondering if you need like an aggregate value, how many clusters or how many outliers I have. All those functions are available within the DBSCAN bundle. So num clusters give you the number of clusters you got, and num outliers gives you the number of outliers. So if we look into our num clusters, we got 5 clusters and 39 outliers. Just so you know, we started with a little bit more than 10,000 records. Now, you might be wondering as well, how do I know if I got good clusters? What are the criteria I can use to assess the quality of my cluster? So Bob has presented the silhouette score. So this is also a function available on the machine learning core bundle, and you can basically look at what is the coefficient provided by your silhouette score. In this case, 0.62. Remember, the closer to 1, the more cohesive your clusters are. Now, there is one important thing I want to highlight in DBSCAN before we conclude. You need to be able, at the end of this process, to add meaning to your clusters. So this is something I usually discuss with Lily, and Lily always emphasizes this. You need to know if the number of clusters you got actually can be translated into something meaningful. And in this case, you can see if I start DBSCAN with the standard minimum points and epsilon values, I ended up getting 22 clusters and almost 5,000 outliers. So this is not good at all. I have too many sparse clusters. That's why my silhouette score is negative. And once I start being more restrictive in the minimum points values and more relaxed on the maximum radio of my clusters, I start getting fewer clusters and a better silhouette value. But again, if I just look at the silhouette value, I end up getting a single cluster, which in practical perspective doesn't make sense for 10,000 properties. So by asking for assistance from someone in the construction engineering area, he was able to look into these clusters and actually start looking at what records were included in each cluster, going back to our standardized values. and start adding meaning to these clusters. For instance, if for some reason records 1, 2, and 3 were added into the same cluster, I could see, for instance, here that record 2 has a very high land square footage. So if more properties also share that same unusual high value, they could be combined in a single cluster that could potentially represent large properties. So that's how you start adding meaning to your clusters, and that's how you can actually end up with the appropriate or optimized number of clusters as an outcome of DBSCAN. Okay, so this is the end of this first tutorial. Just keep in mind we were able to find 5 clusters and 39 outliers, because we will use this information afterwards and look at those outliers more closely using K-means. Okay, so I hope you have enjoyed this first tutorial. And now, Bob, I will stop sharing and hand over to you so you can wrap up the advantages and disadvantages for DBSCAN. Okay.
Thank you, Hugo. Sure, that was wonderful presentation, bringing DBSCAN to life. And in summary now, after I saw what Hugo was doing there, we have our pros or advantages of DBSCAN, which it's pretty easy to implement, and it's an excellent algorithm for outlier detection. It can filter the noisy parts of your data sets, and then based on clustering points in dense areas. Of course, the disadvantages of DBSCAN, there's always a flip side. Not recommended for sparse data sets or data sets with a lot of varying density. And this is, as Hugo demonstrated, the results are extremely sensitive to your epsilon and minimum point settings. But overall, it's a great bundle for clustering. And let's take a look at DBSCAN's brother. Let's go to the next one, K-Means. So classic K-Means, one of the most well-known clustering algorithms. And the word K actually is referring to the number of clusters and based on the number of centroids. We'll get into that terminology in just a moment. So it's a popular method for cluster analysis, especially in data mining. If you have no idea what data you're looking at and you want to analyze it a little bit more, K-Means is a nice tool to do that. It can work with lots of data, and it's very scalable on HPCC systems. All right, so how does it work? The K-Means aims to partition n observations, all right, records into K number of clusters in which each observation belongs to the cluster with the nearest mean. And in other words, another terminology to that is the word centroid. So every point in a data set is part of a cluster whose centroid is most closely located. In simple terms, K-Means means find K number of centroids and then assigns all data points to the closest cluster with the aim of keeping the centroid small. I was listening to a podcast. Interesting, if you ever have any time and you want something on, there's a lot of machine learning podcasts that are out there, and some of them are good and some of them are maybe not as good. But one person I heard, he was talking about K-Means, and he said, he kind of imagined it as like dropping players on a field with coaches scattered in different corners, and players will automatically run to a certain coach on the first iteration. And so a running back goes and runs to a coach and says, "Oh, wait a minute, you're the defensive coach. I don't belong here." So then on the second iteration, he runs over and finds his offensive coach, and so on. So that was a good I thought it was a good analysis, or a good way of explaining it, a good tip. So in the K-Means module, just like in DBSCAN, you start K-Means by setting up a set of iterations that you're going to use for your clustering, and then your convergence tolerance, which I think the default is 1/100%, which K-Means will stop iterating when the center movement of each cluster is smaller than T between 2 consecutive iterations. And then the fit model just takes the output of the K-Means. So K-Means is setting up the model, and then fit trains the actual model. And so you reference the definition of the K-Means. And a lot of times people will nest this stuff. They'll nest it. They'll put K-Means.K-Means.fit, and they'll return the model. And then from the model, you've got a variety of different analysis tools show me my center coordinates, show me my k-centers. You can predict where new data will fall into these clusters based on the model that you've generated. And then analyzing it, you can take a look at the labels. You can look at the number of iterations. And I'm going through this quickly because I'm going to turn it over once again to Hugo, and he's going to go ahead and show you K-Means in action. All right, Hugo, take it away.
Thank you,
Let me
Bob.
stop my sharing.
Let me share here. So, yep. So welcome back, everyone. And in the second part of the today's tutorial, we'll be exploring K-Means. So just to recap where we stopped in DBSCAN, we ended up finding 5 clusters and 39 outliers, but we don't know for sure, if you need to assess those outliers, which one is more an outlier than the other. In a practical sense, you wouldn't need to take your city hall officer to assess all the 39 properties that are considered outliers. There might be one outlier that is more unusual than the other. And the way we can add more granularity into the outlier assessment is by using K-Means. So if we open up the K-Means ECL code, it's pretty short actually. So you can see I start by adding or importing the K-Means bundle, and I'm still using the same training data that I was using in DBSCAN. But as a prerequisite for using K-Means, you need to inform how many clusters your data has. That's why we use a DBSCAN. We now know we have 5 clusters, and I'm adding here the labels or the initial centroids for each cluster. And you can pick those values directly from the DBSCAN result. So if you look at here into the model, for instance, you can pick rec ID 2299 as an element from cluster 5 and 2036 from cluster 4, just as an initial centroid for K-Means. And K-Means will do the optimization for you. As an input parameter for K-Means, I also need to specify how many iterations I want to consider at maximum. I don't want my K-Means algorithm to be running forever and try to find the best cluster or the best centroid. And I'm also specifying some tolerance level here. And I'm not being tolerant at all because I'm using 0. I want to make sure my cluster is not shuffling by the time the K-Means bundle stop. Okay. So once I set up my model by passing the max iterations and the tolerance to the K-Means function, I can then fit my model by passing the centroids information and my training data. And the first result I can extract from my K-Means model is the number of iterations it took to converge, because I want to make sure I'm not being capped by my max iterations parameter. So I took here 15 iterations to converge with that tolerance level, so I'm good to go. And also, I can see how many or how my final centroids are located now. So the centers function receiving my model as an input can give me the final coordinates of the centroids for each cluster. So if we click on the centers tab, we can see here now the 13 attributes from the first cluster, or the cluster labeled as 116, has now these final coordinates. And that's where we have important value from K-Means. I have granularity now to see where each point of my original data set is located in comparison to the final centroids. And I can do that by using Euclidean distance. So we can easily calculate based on these final centroids, looking at the standardized data, you do have here all the standardized values for each of the attributes. So in a 13-dimension space now, you can calculate the Euclidean distance between your final centroids and each data point from your original data set. And that's actually when you start ordering your data points. So that's why I mentioned K-Means can give you some more granularity on your analysis. And now you can start ordering your outliers from the perspective of each one has the larger Euclidean distance in regards to the centroids. Okay. That's one of the usages for K-Means, but I just want to emphasize before we wrap up here that if you're interested to see how many, how K-Means have reorganized your clusters, you can just output the labels from your model. And if you look at the labels tab, you can see that, for instance, K-Means considers now that the rec ID 6 belongs to the cluster 2036. Rec ID 7 belongs to cluster 3 and so forth. So you can also consider that when calculating your Euclidean distance. But I guess the most interesting feature or the difference or something supplemental you can find in K-Means is the predict function. So suppose that you have clustered your data with DBSCAN, you know how many clusters you have taken that information into K-Means, and you have now the final centroids. What if you get a new data set, a new data point, and you want to localize this new data point in regards to your clusters, your current clusters? So you can use the predict function and pass as an input your model, your K-Means model, and the new sample or the new data point using the machine learning data frame format, which is officially called numeric field. And when you use the predict function, you can actually see where this data point will now be or would potentially be clustered if we run a K-Means clustering. So in this case, this data point would probably be tied to the cluster number 3. Okay, so that's a supplemental feature for K-Means that I wanted to highlight. Okay, so that's the end of our second tutorial of today's session. I hope you have enjoyed. Once again, the purpose here is to leverage our bundles in a real life or practical problem solution. If you want to learn more about DBSCAN and K-Means, just a quick tip for you guys, look at your bundles folder and expand DBSCAN and expand K-Means as well. You will see there is some test code, some test data sets you can use just to explore more functionalities around DBSCAN and K-Means. Okay, so I hope you have enjoyed it. Thank you for your attention and see you on the next sessions as well. So Bob, I will stop sharing and we'll hand over back to you so you can wrap up with the advantages and disadvantages for K-Means actually. So.
All right. Thank you so much, Hugo. Wonderful presentation again, as always. And let's wrap it up then with our summary. Again, advantages of K-Means. Works great with evenly distributed data points in equal size clusters. It's very, again, just like DBSCAN, it was simple to implement. And it works well with large data sets. The only disadvantage of K-Means is the starting centroids are sometimes hard to predict. But Hugo showed you he used K-Means as the DBSCAN as kind of a launching board to help him kickstart his K-Means. And so, yes, it is dependent on initial values. And outliers in training data can sometimes skew the clustering. So you might want to remove the outliers when you're working with clustering in K-Means. And you can get those outliers from the DBSCAN results where label was equal to 0. And that wraps us up for hour number 1. I wanted to mention, I did mention earlier, but of course, you have already been through several sessions in the community day. And so in this interface, you have a question and answer stuff. So Hugo and I will stick around here and we'll take a look and answer any questions that you have. Also, then the code that we were talking about is at github.com, that link that you see down on this slide here in community workshops. And there is our personal contact information. So please email us. Let us know how you like this workshop and what kind of workshops you'd like to see in the future. We always want to hear from you. And tomorrow, hour 2, we're going to be diving into supervised learning, linear regression, and logistic regression. So once again, thanks for joining us. We appreciate your time, and it was a pleasure, a privilege, and an honor to present to you. Enjoy the rest of your day, everyone, and we'll see you tomorrow in hour 2. Thank you very much.
Thank you. See ya.